Welcome. In this lecture, I will present some details about engines, how they work, how much work they can produce, and at what efficiency. The internal combustion engine is an engine in which the combustion of a fuel takes place through reaction with an oxidizer, usually air. This happens in a combustion chamber called a cylinder. In cars and trucks, the engine consists of several cylinders, in most cases 4 to 8 cylinders. Other important design features of an engine are how ignition takes place, that is it a gasoline or a diesel engine, and if it is supercharged, like if it has a turbocharger, or if not, when we have a naturally aspirated engine. An internal combustion engine could be of very different design. For most automotive purposes, the engine is a 4-stroke engine, which means that a complete cycle takes 2 revolutions of the crankshaft. The high temperature and high pressure gases produced by the combustion push down the pistons, thus creating work. The work is transformed into a rotating motion of the crankshaft, which is connected to the driveline and the wheels. To characterize an engine, one often refers to its size. This is typically done using 2 different measures. Swept or displaced volume. This roughly is the size of the total volume of all the cylinders, and maximum power that can be produced, given as horsepower or kilowatt, and at a certain engine speed. The work from an engine can be calculated using thermodynamics. A first approach often looks like this. There are no heat losses and combustion is assumed to be instantaneous. The work from such a cycle is the integral of pressure multiplied with volume change, and the work produced is given by the area inside the pressure trace. However, this does not mimic an engine because of a number of reasons. The first is that this is a closed cycle. No air and fuel is flowing in, and no combustion products are flowing out. Therefore, a different pressure volume diagram is needed, where you can see the gas exchange. But again, this is an ideal case. In reality, you would have a number of deviations from the ideal case, giving another pressure trace. Here you can see how the trace is modified because of heat losses lowering the pressure, combustion not being instantaneous but taking some time, and friction losses to get gas in and out, something often called pump losses. In the diagram, you can see how the area inside the pressure trace has decreased, meaning a reduction in produced work compared to the ideal case. Also note that the area inside the gas exchange loop is limited by a pressure trace that goes counterclockwise, so it is negative work, that is, a loss. In the previous slides, it was shown how much work could be produced as a consequence of combustion of the fuel through integration of the pressure trace in the pressure volume diagram. However, this work is not the amount of work you could use for propulsion. To get that, you have to consider losses, for instance, mechanical friction. What can be done is to start with the work produced during the compression, combustion, expansion process, and then reduce this work with all the losses until you have the work which is going out from the engine and then transmitted to the driveline. This engine out work is called brake work and is shown with an index B. So, to find this available or useful brake work, we should start with the work produced during the compression, combustion, expansion process. This is called gross indicated work. Work that is given by the pressure trace in the pressure volume diagram is called indicated work. The next step is to consider a real gas exchange process, that is, with pump losses. Finally, considering losses because of mechanical friction or because of auxiliary work needed to run, for instance, pumps and fans, we arrive at an expression for brake work. In this course, we are mostly considering brake work, since this is what we use in the powertrain, the work we can use for vehicle propulsion. If you make an estimate of where the energy is going, you may get a diagram like this. If 100 units of fuel is supplied to an engine, most of it is lost to cooling of the engine as hot exhaust gases. But it can also be seen how the remainder is divided into useful work and what is lost as pumping losses and friction. It is important to note that this is only one example, not what you will find in all vehicles or under all driving conditions. As said earlier, swept volume and maximum power are often used to characterize the engine. However, there are other parameters that represent the design and the operating conditions. The most important ones are probably torque and speed. Speed is here how fast the crankshaft rotates and can be given both as revolutions per minute or per second, or as angular speed. Torque is a measure of how much work an engine can produce per cycle, and it is often called load. The work produced by an engine is expressed as power and torque, as already mentioned. Power is the work multiplied with how often it is produced. The division with 2 in the first equation is because it is a 4-stroke engine, and work is only produced every second revolution. The next relation, the one between power, engine speed, and torque, can be derived using the knowledge that power is equal to force multiplied with speed, and that torque is equal to force multiplied with radius. One reflection here is that torque, or load, is the ability to perform work, but power is how often you can do it. Finally, another parameter is introduced called mean effective pressure, MEP, which is defined as work divided with swept volume. If the work considered is brake work, the mean effective pressure is called brake mean effective pressure, BMEP. In the slide, the relation giving the brake mean effective pressure is given, but as a function of torque instead of work. What one can see is that BMEP is proportional to torque, or load, and BMEP is often used to describe at what load an engine is operated. For a naturally aspirated engine, that is, with no supercharging, full load is equal to approximately 10 bar. Bar is here used as the unit since it is convenient to use simple numbers. Also, an engine running at 2 to 3 bar is running at low load. The reason there is a maximum load or amount of work an engine can produce is that it is about how much fuel you can burn during a cycle. And combustion is a process that needs not only fuel but also air. There is no problem to add more fuel, but air is restricted by how well the engine breathes. And a consequence is that the maximum load of an engine is determined by how much air you can get into the cylinders. So, if you want to increase the amount of work an engine can produce, you have to supply more air into the cylinders, and this can be done using a turbocharger. The next relationships concern efficiency. How much work do we get in relation to what we spend? That is, the fuel flowing into the engine. Efficiency can, as shown here, be given as a dimensionless efficiency value, the so-called fuel conversion efficiency. How well can the engine convert fuel into work? This parameter is independent of fuel. There is a second relationship, giving the brake-specific fuel consumption, BSFC, usually with the unit gram per kilowatt hour. This parameter takes into account what fuel that is used, so a fuel with a low heating value like ethanol gives a higher value of BSFC than, for instance, gasoline, even if the ethanol engine could have a higher efficiency. So far, I have presented a number of details about engines, how they work, how much work they can produce, and at what efficiency. And the engine have different properties in different operating points, that is, different combinations of load and speed. In this slide, you can see an example of engine performance, in this case a gasoline engine. The plot shows load given as brake mean effective pressure versus speed given as revolutions per minute, and how efficient the engine is in these different points. Efficiency given as brake-specific fuel consumption. First, what you can see is a line of the maximum load as function of engine speed. The engine can operate anywhere below this line, but not above. And as stated previously, the maximum load is determined by how much air you can get into the cylinders. There are also limits regarding engine speed. In this case, the limits are 900 and 6,000 revolutions per minute. These kind of plots are very useful to describe how an engine can or should be operated. For instance, if fuel consumption is the important parameter, you would like to operate the engine in a point with as low BSFC as possible. In this case, you can see a small area at 8 bar and 2,500 revolutions per minute, where the specific fuel consumption is below 260 grams per kilowatt hour. So this is where you would like to run the engine. You can also see that there are areas at very low load, 1 to 2 bar, where efficiency is poor. The brake-specific fuel consumption is very high, and this because of high pump losses, one of the processes that reduce the available work, as mentioned early in this lecture. Much work concerning engine development is focusing on techniques and technologies to improve engine efficiency, but also on how to be able to run the engine in favorable operating points. Okay, I think I will stop here. Thank you for watching.